Okay, this next lesson's on a velocity time graph, which is a little bit different from the position time graph we looked at in the prior lesson. Same guy here, going to just be on linear motion, positive direction, negative direction. This time we're starting in a negative direction. But this time our graph's going to have velocity on the y-axis as an independent variable and time still on the x-axis. So what I'm going to do is move them through a few motions. First, trying to keep him a constant. Second, trying to give him a uniform acceleration rate, and then do something with him turning around, look at each part. Now this graph's going to be a little bit more jumpy than before just because I'm controlling them with my hand, and usually VT graphs that are real sensitive to acceleration aren't going to be nice and smooth by me manually doing it, but I'll do the best I can. Alright, so let's take a look at what happened on this one. Now remember, this is not a position time graph. Let's look at first the few, a little bit less than 2 seconds that before I started moving, I was flatlined at 0. Remember, this axis is velocity in meters per second. So a flat line at 0 means not moving. However, a flat line anywhere else just means a constant velocity. Now this isn't very flat right here from 2 to 4 seconds. Like I said, it's going to be a little bit jumpy because my hand's not perfect going constant, but it's pretty darn close. Smooth that out, line of best fit right there from 2 to 4 seconds. You got a pretty flat line right there if we average that out. And that's a little bit above 0 and staying pretty steady, flat. So flat on a, or horizontal, anywhere away from the origin on a VT graph just means you're at that steady velocity, and of course I was moving in the positive direction when I began, so that's why it's above 0 on the y-axis. Then I tried to maintain what we call uniform acceleration. That means I was speeding up, increasing my speed from a little bit over 0. Looks like I was at about 1.9 roughly at 4 seconds. Then I decided to speed up till I peaked up here at roughly 9.4 meters per second. Again, not a nice smooth line, but averaging out that jumpiness, if it was a nice straight linear line from there to there, I had a fairly consistent, uniform, or constant acceleration. Be careful, because constant acceleration means I'm speeding up at a uniform rate. It doesn't mean constant velocity. Don't get those confused. So what we could learn from this, imagining if this was nice and straight, any linear line we could take the slope of, and our new acceleration equation, which will be a equals final velocity minus initial velocity over t, comes from the slope of a velocity time graph. Change in y or velocity, change in t, change in x is really time in this case. And then what I did was a quick reverse of direction somewhere over here, and you could see it drop. And actually, that quick reverse of direction stayed fairly linear. So I could find the slope of this graph down to wherever it may have went. Let me zoom out, actually, to see it. I guess that's the best I could do. But this line represents a negative slope, which means during that process, if I calculated slope, I'd have a negative acceleration rate. And I completely changed direction because now all these lines, even though they're all crazy and overplaced, notice are in the negatives. That just simply represents I was going in the negative direction. So there's a few things about VT graphs, but be careful and don't get those little features confused with PT graphs. One little quick thing worth watching is to now look at an example of both position and velocity time graphs over top of each other. So I'm just going to do some random motion like we did in the last 2 lessons, and notice there are big differences here when they're directly displayed on top of each other, because many of your actual labs will have 2 graphs like this on top of each other. And I'll stop it. So let's look at one over another. You can see we're pretty linear through here, meaning on a position time graph that I'm going at a constant velocity or pretty darn close for that time. And we do have a little spike down here. down here I have, and looks like a pretty good one, from about, let's see, 3 seconds roughly to about 7 seconds. Again, linear on this graph means constant velocity because that's what the slope of it represents. And look how that, especially down here when considering both of these, my velocity stayed with a little tiny jumpiness at a constant negative, what's that look like, negative 2.3 or around that. So we could see constant V on this graph is flat, but on this graph it's a linear slope. I also got a little bit of curvature over on this side, if you remember. That represents an acceleration if it's curved, and an acceleration, if we look right below on this one, if it's uniform, should be somewhat linear, a little jumpy, but not bad through there. So just how to read from one graph to another and determine what's going on. They're not quite the same, but some features we can tell from each of them. It's just how they're shaped is a little bit different.